right? We need to understand a quantity. All right. So let's say I have somebody, right? Let me see. Somebody who knows how to mess. You don't really move so much, right? Let me take a look at. Let's take a look at somebody else. Let's look at Jude, right? So let's say Jude starts here, right? And Jude moves here, right? If Jude moves this from here to here, Jude would have covered a distance, right? The distance Jude would have covered, let's say, is 5 meters, right? If Jude then went from here to here, let's say that's 4 meters, then Jude would have covered a total distance. He would have covered a total distance of 5 plus 4, which is 9 meters. All right. But then sometimes we use a quantity called displacement. Right? What displacement is, unlike distance, distance is like the total length traveled. All right. Displacement, on the other hand, is the straight line distance from where you start to where you finish. So Jude's total displacement would have been from here to here, whatever that is. That's okay? So I want you to understand the difference between distance and displacement. Anybody remember which is a vector, which is a scalar? Which is a vector, which is a scalar? Yeah. Right? Direction matters, right? So you have to start and finish. Right? So once I give you specific directions, then vector, scalar. That's okay? So if you look at the note, distance is the total length traveled by an object. SI unit is meters. Displacement is the total distance traveled in a stated direction or the distance from a starting point, right? From where you start to where you finish, right? That's okay? How fast you move now has to do with the speed. The speed of an object is the ratio of, so if I ask you about speed, is the ratio of your distance covered with respect to time. SI unit, ms minus 1. Right? Velocity, on the other hand, because velocity is a vector quantity, you will see here that your velocity is your displacement over time. Right? So your velocity direction matters. Okay? So your speed direction doesn't matter. Right? And they have the same SI units. So if somebody asks you what is the difference between speed and velocity, what you'll tell them? Antonia, what you'll tell them? You know, I'll pick up. What you will tell them? What's the difference between speed and velocity? Right? Speed has to do with distance. Velocity has to do with displacement. One is a scalar, one is a vector. Right? So speed has no direction. Velocity has direction. Right? Remember the usual thing. If you go one direction and you change the direction, it becomes negative. One positive, one will be negative. All right? Right? If the velocity of a body is constant, if it moves with steady speed in a straight line, if either of the speed or the direction changes, the velocity will change, right? And there is this very popular example to show that an object could have constant speed, right? But changing velocity. Anybody knows that example? Constant speed by a velocity changes. Talia? And where are you going? Huh? How can your speed be constant, but your velocity changes? You want to guess, yeah? Change in direction. And a perfect example is a circle. Right? If you had an object moving in a circle, you'll recognize same speed, same distance with time, it's the same. But the direction on top here, because it's a circle, the direction is always a tangent. The direction is like that. When you're here, the direction is like that. When you're here, the direction is like that. When you're here, the direction is like that. So what you recognize? Although you move with a constant speed, the direction always changes. That's okay? Yeah? Alia? Alia. Not Alia, only not Alia is Raya. Anal. Anal. By that, let me color up. So your direction changes. Okay? So once the direction changes, you have a changing velocity with constant speed. Okay? Perfect example is a circle. Moving in a circle. Okay? Yeah? Right. Oh, wait, let me get underneath it. So an object moving in a circle constant speed, right? Underneath here, suppose I have a diagram. All right, so next thing that we need to remember is that we need to also know that, how to change units, right? How to change from meters per second to kilometers per hour, right? How do we change from one to the next? So how to go from kilometers in an hour to meters per second? Because sometimes your SI units will be in kilometers, but you have to convert. All right, so it's real simple. All you have to do is multiply by 1,000 and then divide by 3,600. Right, so watch it here. For the shortcut, multiply by 0.26. All right, anyway, I don't think I tell you what to do. So kilometers per hour to meters per second, write it down, multiply by 0.27 and meters per second to kilometers per hour, multiply by 3.6. Right, so if I give you kilometers per hour and a second to meters per second, that's what you're doing, right? Multiply by 0.27. Right, I think I'll two for you to try here. Oh, sorry, just one. Yes, two. Try this, please. Someone watch it. Right, how much you got? You multiply 90 by what? So I got a 6 part here. That's a mistake. You want to convert 90 kilometers per hour to meters per second. That's a little mistake here, right? So to reach here, what you doing? You multiply by what? 0.27. What you got? 24.3. Right? 24.3. We get 25. And I get 25. What did I get? What about that? Yeah, the way. Okay. Okay. All right, next one. I don't know what happened. Convert this next one here. 30 meters per second to kilometers per hour. Right? So show that this is correct one. 108. Yeah. 108. All right. So I have a small question here. In this question, we have a car. We have a car. 108, right? And we got 108. Yeah. No. Together. 10.8. Multiply 30 by 3.6. Remember, you're going meters per second to kilometers per hour, right? Right? So there's this question, right? With a car, and the car is moving with a speed of 50 meters per second. Right? But the speed limit is 100 kilometers per hour. What will happen to that person? There's a police right outside. Right, and right here will have the police. What will happen? Ticket or no ticket? So you can work it out and tell me if you'll get ticket or not. What is going to happen? Ticket or not? Ticket? How much is 50 meters per second in kilometers per hour? 100 and 180. Yeah, we'll take it for sure. Right? Take it. Right? Because it's more than, right? Antonius? You okay with that? So what you learn, Antonius? Huh? No, I mean to break the speed limit. Right? That's what that's right? Don't go so fast, right? Right, so nice. The problem here is that they were not in the same unit. They have to learn the conversion. Where does it happen a lot? But besides on the highway, you ever recognize it for those who could travel? Like in the state, what do you measure this speed at? Miles, right? Right, so to be able to compare speed limits, you will have to convert one to the next. All right. All right, there's a next quantity that we need to learn. It's called acceleration. All right, what is acceleration? So acceleration is the rate of change of velocity. So you're basically measuring how an object's velocity is changing with time. Right? Changing velocity means final velocity minus initial velocity all over time. That's the formula right here. Okay, so acceleration is change in velocity with respect to time. SI unit, ms minus 2, and acceleration is also a vector quantity. Okay, acceleration is also a vector quantity. All right. The next thing that we need to know is that when an object is changing velocity positively, it is accelerated. When the velocity is changing negatively, it's called deceleration. All right. So if you have a man here and he's running, right? And he ran from 4 meters per second to 6 meters per second. What you'll say? Accelerating or decelerating? Accelerated, right? Because it increases. His velocity changes positively. But if it goes 14 meters per second to 6 meters per second, slowing down, right? So it changes negatively, and that is called deceleration. All right. Let's look it up somebody online. Alexandra, you there? Yeah. Oh, okay, okay. You gonna come in front? There was space there everyone. You don't want to see the board. Hamlet. Hamlet, come back again. Hamlet went to the bus. What happened here? Hamlet, you reach back? Yes, sir. Right, Hamlet. Here's the question, right? Suppose the velocity not changing. What will happen? So suppose this guy here running, right? His velocity is 4, and a little while after it's still 4. What happened then? See that over? If his velocity is 4 initially, right? And a few seconds after, his velocity is still 4. What is happening? What is happening to the cursor? Accelerating, decelerating, right there. Maintaining. All right, but it's true. He not accelerated, he not decelerated, but his velocity constant. Right? So he has constant velocity throughout. That's okay? So therefore his acceleration is what? Right? He's still moving, but he has no acceleration. Okay? All right, now take a little read here. I don't want you to give it a try. Try that one, please. Upside down. Huh?
Really?
Make sure you have the right SI unit there. Right. So the object starts from rest. So it means that the initial velocity is 0. Final speed is 6. So it means that v is 6. And the time it took is 3. But what do you want to find? Find acceleration. How is find acceleration? V minus u all over t. So that is 6 minus 0 all over 3. So that's what? 2 meters per second squared. All right? Easy, right? Yeah. That's it conventional we use. So initial we use U for initial and V for final. S for displacement, A for acceleration. Right. How do we represent all this information? So sometimes we can represent this information using time graphs. And there are two types of time graphs. A displacement time graph and a velocity time graph. Okay? And there are two important things that you must know from the graph. If I give you a displacement time graph that looks something like this, we need to know that all these gradients here, this gradient, that represents velocity. Right? So the gradient on a displacement time graph is velocity. All right? Look at this graph here. Anybody can tell me, hold on. Anybody can describe what is happening on this graph? Let's say here's O, here's E, here's B, and here's C. What is happening on this graph? O to A is what? Person moving? Yeah. So O to A, the person is moving with constant velocity. Right? But A to B, the person distance staying the same time. So it means that the person is what? If it distance staying the same, but time going, it means that you're not moving, right? So it means that the person is stationary. All right? How about here? Distance moving and time changing, so your person moving, right? But what? Not? Right? So we're getting negative velocity. So what does that mean? It means that we change direction. Right? Right? So a negative value for velocity or a negative gradient means the change in direction. Make a note of that. A negative gradient on a displacement time graph means a change in direction. Okay. Add the person name here. I thought somebody knew. That's back then. And add the monthly let's start doing it. All right. So that's the displacement time graph, right? The most important thing is what the gradient gives you. The gradient gives you velocity. All right. Next one, a velocity time graph. Right? This here is the general shape of a velocity time graph. These are the important things on a velocity time graph. Number one, gradient gives you what? Gradient gives you acceleration. Number two, negative acceleration, deceleration. So we know that already. And number three, the area under the graph is distance covered. So you can only find area under a velocity time graph, right? Not the first one. So the area under velocity time graph gives you distance covered. Now you have in your note, but let's make a extra note. Actually, put in diagram. Right, if you put in a diagram, the area underneath here is equals to this distance traveled. Right, if you look at this graph, it shows you all the way up until here, acceleration, all the way down here, deceleration, and here, no acceleration or constant velocity. Okay? Are you okay with that? All right. So here we have some information. What you have to do from on that information, you have to get a graph and then find a total distance traveled. right? Take a little read, right? Right, read it, catch a graph, find the gradient. Right, let me see Devana, Nadir, Bandina, Chloe. You don't hear any name other, right? Nathan, Aidan, Annalie, Zakaria, Shavanan, Adam. Thing, Adam. Annalie, Tishon, Alexandria, Sherelle, Attilia online, Carisha, Caria, Anya, welcome to that again. Ansari, that's the boy we have. He left the come Christian here, Gianna, Maria, Caroline, Malia, Cornwall. Joy, Peter, Chelsea, Watson. Right, so you want to sketch a graph? What type of graph? A velocity time graph, right? So do a quick little sketch and put the points and then connect it up. Started from rest, ran to a velocity, ran a distance to 25 meters to reach a maximum speed, maintain the maximum speed, and then decelerate it back down. So it follows the shape of the one that we probably did before, right? Let's try and put in the values and then find the distance. Finish it. What is now? I think I will put it in. Now you do it last time. I have to do it and I'm on quick, right? All right, so let's check out your diagram. Oh. Right, so it started from rest, so we know it started from here. What is the speed it went up to? Annalie, what speed it went up to? 30. So it went all the way up to 30. And then how long it took there? 25 seconds. And then what happened there? Right? It maintained that speed for 1 minute. That's 60 seconds, right? So what the job meaning? A straight line? Is that straight line? Horizontal line. So draw a horizontal line. What will time here? What will the time down there? Huh? It's a minute, right? So it's a minute plus 25, 85. 85 seconds. Yes? Remember, it maintained it for a minute. So after 25 seconds, you had 60. Oh. And then 45 seconds later, tell you the game erupts. So how much time is that now? 45 plus 85, right? Which is 150. So a completed graph looks like that. And I not see the bottom, but that's 150. I just have it because I'm going to show you something now. That didn't help. No, so sorry. But the values are 25, 85, 150. Now they ask me the total distance traveled. I just find the total distance traveled down. I just find the total distance traveled Shivanan. Okay, but the last graph I made you right. I just find the total distance traveled. Find the total area. Right? Find the area. Find the area of that shape there. And you have two options. Trapezium law, or you can do what? Trapezium, or you can break it up into a rectangle and triangle. All right? Yeah? Work it out fast. Anyone you want, you can use. All right, let's what you got. I am using the A worship piece here. What's the formula for A worship piece here? Half the sum of the parallel side by the height. So it's half the sum of the parallel side. That's here and here. So that's 130 plus 60 by the height. Right? The height is here, which is 2. How much is that? What y'all got there? Anybody else? Yeah? You all get up. All right. 2850 meters. Any questions online? Any questions earlier? Or look at that? So remember, even if you don't remember the PTM rule, you can break it up into 3 shapes, right? 2 right angle triangles and a rectangle, right? So you can break it up a little bit. Malachi, stop messaging me now, boy. We keep keeping this person Ronaldo around the side. Right? You will start to pay Peter Ronaldo around the side. All right, let's go again.
Anybody have any favors, any offers?
Anybody have piece of play?
Okay, come one time, because what you gonna do, right? Close the gate, please.
Before you go out up there, right? Hold on, I don't know why this. Right, we're gonna take a look at the past paper. It's Jan 2002. Right, for the paper, they can go fast, right? All right, good. Should be able to see it now, right? This is 2002 paper 3, number 1B. Huh? Who? What's up? Yeah. Look at it. Take your time, get the graph, and let's give it a little try. See? Right, you don't use graph paper. That's part of the right? So you get just like it out. Progress, right? Feed up four, right? So most of the questions kind of follow the same shape, right? So read it through, catch it, put in the values. All right. 5 minutes, that's going to be worked out this whole thing. You don't need graphing, all right? Yeah, sure. Right, Antonio, well, we're talking board. Oh, yeah, let's sort out. Right, all those who doing exam with us, right? Even if you're not doing, anybody not doing lab or doing exam with us? Not doing lab or doing the exam? No, everybody doing lab and the exam, right? I'm gonna organize something a little different to it, right? I'll talk to you after this class. Anybody online? Anybody online doing exams with the school? And labs? Hopefully not, right? No? Alright. Alright, so let's go to this question here. Alright, let's go to question here. Right? Right? Those who in school, how far you reach? How far? Right, like around here. How far reach school? Right there? Right here. You don't know where you reach? Huh? Alright. Alright, and all the people who write in next year, we have to argue also our LMS, where I have all my notes and videos, and I want to also do other faster than this. Alright? Are you sir? Are you sir? Alright? Alright, part B. So, right, so the elevator of a high rise starts uniformly from rest. Right, starts uniformly from rest, speed of 4 in 2 seconds. So a speed of 4 in 2 seconds, right? You unit here, so I don't have to write it. Right, it then continues at constant speed for 4 seconds. Constant speed for 4 seconds. Don't write 4 here, it's 2 plus 4. So it's 6. And thereafter decelerate uniformly, come into a complete stop in 3 seconds. 3 plus 6 is 9. So your graph will look like that. Okay, that's the first part. Part 2, calculate the acceleration in the first 2 seconds. Right? Calculate the acceleration in the first 2. So we just need gradient of v minus u1t will give you the same thing, right? V is 4, initial velocity is 0, time is 2. So the answer is 2 meters per second. Right? Or you can just find the gradient and you'll get the same answer. All right? Yeah. Find the distance traveled while decelerating. Decelerating is where on the graph. Right? Decelerating is here, right? So you want to get the area there. You want to get the area there. It's a right angle triangle. So it's half base, which is 3, by the height, which is 4. So half of 12 is 6. Okay? Half of 12 is 6. And then they want the total distance traveled. What will be the total distance traveled? So look at that. Machine can do rubbing off. So rub off one fixed part 4 2. Right up, right on. Anybody want drops? What? You want drop? I'll come here. All right, you get this question right, then you'll get it. Take your time. Sorry. Are you done? Yeah. Okay. But yeah, I you have to grow. Okay, that's the baby does. Yeah. All right. So let's see what will the area be, right? So the total area is half the sum of the parallel sides, that's 9 and 4, by the height, which is 4. Right? So this is half of 4, which is 2 by 13, which is 26 meters. Glitch up, glitch up again. That's a sign. I'll get the next one. All right. So what do I want you to do for me is going on with this thing, right? Right? What I want you to do for me is one more. What time is it? Probably don't have that. 20 plus. Right? The same as what we want to do. Right? So the next thing that we have to move on to is all the load, right? I sent you all the handles. I want you to read up on the load. Right? Who's load? Newton's laws, right? So there were 3 guys: Aristotle, Galileo, and Newton, right? I don't know. Just so started. Aristotle, Galileo, right? Wait, you buy a labo? Buy a labo? All right, nice. All right, good thing time. Let's up here. Yeah, Aristotle, Galileo, and Newton. And I was song with them. All right, just one more thing and we're done, right? All right. So the next thing I want to quickly look at, we want to take a look at the laws of motion, right? There were these 3 guys. Firstly, Aristotle, right? Of course, he looked at motion, he investigated motion, and he observed, based on his observation, he thought that force and velocity were all proportional. So if you have an object and you want the object to move faster, right? You have to just apply a greater force to it. Right? That's what Aristotle thought. And once you apply a greater force, the object will move faster. But that's not always true. Right? Think about on a flat hill, right? On a flat, sorry, not flat hill, a road. Right? And you apply a force to it, it'll go faster, right? But suppose you're going up a hill and you apply a force. Would you necessarily go faster? No. You might just be able to maintain the same speed, right? So what Aristotle was saying wasn't always true. All right. And then Galileo came along, right? And then Galileo kind of laid the foundation for the laws that we know today called Newton's laws, right? Galileo, he challenged many of Aristotle's views and replaced them with the following: a body keeps moving with uniform velocity if no force exposes it. It should be no force acts on it. I should expose it. Anyway, so it will continue with a constant velocity if no external force acts on it. And he predicted in the absence of friction an object is basically more efficient. What you kind of know now, right? No friction, it'll be more efficient. All right, and then this guy named Newton, which is what we know now, he had these three laws, right? Newton's first, second, and third law, right? So your homework, I want you to read up on all of them, okay? And there's one question here you can try. All right, but before you go, I just want to just run through the laws so you have an idea of what you're going to read. All right, so here's what Newton here are basically Newton's three laws, right? That's not it, it's lagging out there. Better now, right? So here's what Newton said. Three laws, right? Newton's three laws are basically this. If I have an object, let's say I throw that object. That object will continue to move in a straight line with constant velocity, unless an external force makes it behave differently. So this object will come off in part if an external force acts on it. What's the external force action on an object? In the air. Weight, right? So because of weight, it will come off of this path. That's okay? But Newton said if there was no force acting on it besides the one you applied, it will stay in a straight line. Right? Like in space, if you throw a ball in space, it will stay in that straight line. All right? That's why like rockets, when they enter space, they can remove thrusters. Right? Because they will stay on that course. All right? Newton's second law now, that's the hardest law. What it says is this: if I have an object of a mass, and that object has an acceleration, then in the same direction, Talia, it has a resultant force. Okay? If it has an acceleration, it has a resultant force in the same direction. But if this is zero, then it has no resultant force acting on it. That's okay? So Newton's second law, summarized by F is equal to ma. And Newton's third law is the one that you're experiencing now. If you have two objects, one is applying a force on the next, then the next object applying an equal and opposite force. So like you're sitting, you're applying a force on the chair, and the chair is applying an equal and opposite force on you. Right? That's kind of why you can feel the chair. All right? And that is Newton's third law. Right? That's what this is A and this is B. So the force on A is equal to the force on B, but in opposite direction. All right? Your homework is to read the three laws and give two examples of each law. Real life examples, right? Of each law. So you have to figure out where is observed this and where is observed this and where is observed this. Okay? You didn't write it down. Yeah, write it down. Or you can bring a quick. Right? Right here, homework, read about those laws, and we will take a look at those laws and do some calculations on those laws next week. Two examples for each law. Aristotle and no, because